very content. I'm doing pretty solid. I had the best night's sleep I've had in weeks last night. I was dead to the world. I don't remember dreaming. I don't remember turning over. I don't remember waking up. But man, I was out. So I'm doing pretty good. I'm as close to a 1 as I probably ever am. So oh, Bethany's got it ran down today. She's kind of doing okay. Tyson's up there though. He's got that. He's just real close to 100%. He's at 98. So feeling solid there. Cool. Here, I got another one for you guys then. This one's just 2 choices. 1 or 2. Would you rather have unlimited free Wi-Fi forever or your battery never loses its charge? 1 or 2. Make that an easy choice for you. 1 or 2. Alex says, I want that unlimited free Wi-Fi. We got one sentence. That's the last class. Everybody chose the same thing. Everybody in the class chose the same thing. Nobody chose. And they all chose 1 last time. Everybody chose the free Wi-Fi. I don't know. I think I would be more towards the battery never losing charge. Man, my battery, I didn't have to worry about that ever. Man, that would be awesome. Battery never loses charge. But either way, I can see both arguments. Don't have to worry about not having Wi-Fi. You always have your phone always can access the internet, any of that good stuff. Absolutely. All right, let's go look at our lessons. We got a lot to cover. 5th hour. Let's go to our grade screen as usual. If we scroll way down here to the bottom, all we see is 2 assignments. 4.03 and 4.04, polynomial transformations and solving and graphing polynomials. Those are due this week, and that is the last assignments until the final, which I don't have the final on there. I haven't decided if I'm going to put the final on Buzz or use a formative on that, so I haven't decided what I'm doing at the final yet. But I'll have that up there. Next week when we meet in class, we'll talk all about the final. We'll be good. And you'll see over here, we do have 1 lesson. If I go to activities, 4.03, 4.04 today. There's also a 4.05, but there's no assignment for that. So we'll briefly hit that next week and talk about the 4.05. And there is a review and not really a practice test. There's a review on here, which goes over all of these lessons and just gives you a summary of them for the final, basically. There it is. Long division, theorems of algebra, polynomial, and even next week's. So you can go to click on that and get basically the lesson summary from those all in one place. All in one place for you. Except mine's not loading. Look at that. It says it's loaded because it's scrolling up and down, but there's nothing there. Let's try that again. There it is. So it does have the lesson summaries from the whole unit right here on that last 4.06 thing. All right, so we're going to look at this week's lessons, 4.03, 4.04, so you can do the last assignments of the semester and get ready for the semester final coming up here very quickly. All right, 4.03, polynomial transformations. Now, we've done transformations. We've done transformations of quadratic equations and all kinds of stuff. So we're just talking about any polynomial at this point. So graphing polynomial functions without technology, which we have Desmos all the time in here, really. So graphing on a coordinate plane has adapted along with your skill in math. I mean, you started out back in like middle school with a graph, and it's a graph the point 2, 3. And so you'd have to go to your graph, find where x equals 2, and then move up to where y equals 3. You'd put a little point and label it 2, 3. That's where you started graphing, way back when, years ago. Then you got to where, by junior high, you were graphing lines. Y equals mx plus b. Y equals 2x plus 1. So I go to that y-intercept at plus 1. And then I graph a slope of 2. I go up 2 and over 1, put another point, get my ruler, draw lines. Quadratics, parabolas, we graph those now. Now we're even into some higher degree than that, polynomials. So here's a quick review on graphing a line. If you needed that, you can make a table. You always make a table, -6, -4, -2, 0, 2. Plug in those values into the equation to get what the y equals. And you can connect those points with a line. That's another way to do it other than just taking the y-intercept and the slope. You can graph some points, connect them with a line, or you can do, here's the method I was talking about, where you say if it's 1/2 plus 5, you take the 5 as the y-intercept and go up 1/2 and graph the next point and then connect them. Notice it's the same graph. Same graph. So graphing parabola. We did that with a table. Generally, when you're doing it by hand, you find out where the vertex is with that -b/2a. It kind of tells you where the middle of your parabola is, which in this case, it was at 2. You find the y was -1 when x is 2. So then you would use the vertex as your center of your table and graph points on both sides of that. Substituting those values in, and then just putting those on a table and connecting them with a curved line. So we've graphed parabolas, we've graphed lines. Now we're going to talk about graphing higher degree polynomials. Like a third degree polynomial is called a cubic function because you're taking the cube of something. X cubed, x to the third power, also known as x cubed. So the graph of this function is choose some x coordinates and substitute them in, like still making a table. We can make a table for any graph, basically. Just choose -2, -1, 0, 1, 2. Substitute those numbers into the equation, x to the third power. So you take all of those to the third power, and you get -8, -1, 0, 1, and 8, which they show you on this table. -8, -1. And there's the calculations above, taking each of those to the third power. Then you put all those points on the graph and connect them with a curved line. -2, -8, -1, -1, 0, 0, 1, 1, 2, 8. And so your cubic function looks pretty much like that. And that's before you do any transformations. So remember, we've talked about transformations. You can put a number in with the C, and that's going to move it left and right. Horizontal shifts. Right? It'll move left if it's x plus C. It'll move right if it's x minus C, or whatever that C number is. We've also used H and K for these transformations, right? X minus H, X plus H. When we put it at the end, plus C, just putting a number at the end, that's a vertical shift, right? It moves it up if it's a positive number we put, and it moves it down if it's a negative number. And then these work very much the same. If you put a multiplication number times x, or put it out front as a coefficient, either way, it's going to multiply and make it either be wider or more narrow, depending on whether that number is bigger than 1 or less than 1. This will also make it wider or more narrow. So both of them will make that type of, and if it's a negative number, it'll reflect it downward, right? Flip it upside down. See, if it's inside, if it's a negative number inside with the x, it actually reflects it over the y-axis. That's the only difference between those two, is the y-axis or the x-axis, whether it's a coefficient or in with the x. All right, so for example, it talks about graphing the cubic function of x plus 2 over 3. I mean, to the third power. So we know to the third power. We saw that up above right there. That is the graph of that. This, we should recognize, is a horizontal shift. That should be the exact same graph, but shifted 2 units to the left, since that's positive. Let's look at it on Desmos. Make that quicker for us, because it will take a while if we do it all by hand in here. And we've only got an hour and a half. There's the x to the third, right? So now if we do the x plus 2 to the third power, it's a shift to the left. That turning point at 0, 0 now becomes a turning point over at -2, 0, because it just shifted the whole graph. Everything went left 2 from where it was originally on the green graph. So they do that by hand here, finding the turning point at x equals -2, making a table, finding the y values for that table, and then plotting those points and connecting them with a curved line. So same way we can do any graph, we can put some points and then connect them. A quartic function. Quartic, that's a fun word. Remember that when you play Scrabble, you're looking for that Q and what to do with it. Make it quartic. This is a fourth degree. Right? X to the fourth is a quartic function. So again, you can select the x coordinates, find the corresponding y's that go with that, and make a table. Then you can put the points on a graph and graph that. So if we go to Desmos and look at that, a fourth degree function, oh, it made it a subset instead of a, there we go. Looks a lot like a parabola, except it's flatter at the bottom. Flatter at the bottom. If we said a parabola, x squared, notice it's more like a U, I'm like a V, closer to a V. It's not a V because the V is an absolute value graph, but it's different. The fourth degree is more narrow as it goes up, but it's flatter at the bottom. And we'll see that more the bigger that gets. If we say it's a 14th degree, wow, it keeps doing that thing to me. See, 14th degree is really flat at the bottom and goes up a lot steeper than the parabola. So it just depends. But the fourth degree is flatter, but behaves a lot like a parabola. All right, so here it goes. You may be thinking the graph of a quartic function looks like a parabola. You'd be right. It does look like a parabola, but that's not the case for every quartic function. If you add more terms to it, like if we put an x to the third, and an x squared, and an x, and those type of things, say minus 3x to the third, see, now it no longer looks like a parabola. Now it looks pretty weird just by adding an x to the third term in there. And then we put a plus 4x squared. Now it's closer to that. What if it's a minus 4? Oh, see, now it's even more exaggerated way down there. Plus x. Now it's dipping down on the other side. So it starts to look less and less like a parabola the more the other terms are filled in. But if we just have the x to the fourth, we have that parabola shape looking once again. All right. How about graphing x to the fourth plus 3? Well, we know that plus 3 on the end should just shift it upward. Plus 3. Exact same graph. Every point is shifted upward 3. So let's remember how these translations work the same, whether it's a fourth degree, whether it's a third degree, whether it's a quadratic, or even if it's just a line. Have you ever thought about that? A translation works the same with a line? Let's turn that off. Let's see. So a line would be like y equals 2x. Translation. If we add a minus 3, it's going to shift it down 3. Instead of 0, 0, it's now down to 0, -3. So translations work the same. How about it the same with the x? If we put an x minus 1. Oh, I didn't put it in the right place. Minus 1. Look, it did. It shifted the graph right. It wasn't going through 0, 0. It just shifted to the right. So translations work the same even with a linear equation. Linear, quadratic, to the third power 4. It doesn't matter. Translations will always do the same things. All right, so we're going to make us some notes here, because end behavior is something that you're always going to be asked in a math class. We talk about end behavior. So let's make us a table for our notes to talk about end behavior. Is my light on? No, it wasn't. Okay, here we go. End behavior. So if you take notes, you can use them on the final. You can use them on quizzes. You can use them on tests. You can always use your notes on any of my assignments. So for end behavior of a polynomial, let's talk about two different kinds, because one of them would be if it's an even or an odd. Now, we need to be very careful what we're talking about when we talk about an even or an odd, because we're going to talk about some other even or odds later today, which is totally different. So when I talk about even or odd, let me change my little divider here. I'm talking about the largest exponent. Largest exponent. Is the largest exponent an even number, or is the largest exponent an odd number? Okay, so that's our dividing point first off. Okay, now let's talk about the coefficient, because that's going to affect things. Coefficient. Okay. And the coefficient over here. All right, so we're talking about the coefficient. Now, the coefficient, remember, is if we have an equation, if we're talking about 3x to the fourth minus 2x squared plus x minus 1. If we're looking at this, the coefficient is the number that's in front of the variable. This actually has three coefficients. We have a coefficient of 3, a coefficient of -2, and a coefficient of 1. We don't write 1 when it's a 1, but that's what that coefficient is. Coefficient of 1. So for this, we're looking at the largest exponent and the coefficient just of that. So for this, we only care about this term. This is the boss. This is the big daddy. Whoever has the largest number with the exponents is in control of the graph. These guys can affect the graph, but they do not have control. This is going to determine what the graph looks like. And we're talking basically about the ends of the behavior, the end behavior of it. So this coefficient. So looking at the one we were just looking at there, let's say it was 3x to the fourth, and let's just do -2. We won't make a long thing. This is even. Even. That's an even number. 4 is an even number. We learned that back in grade school. We're going back to our grade school math today to figure what's an odd number and what's an even number. All right, so if the coefficient, and I guess I'll do this in blue. Is positive or negative? Okay. And over here, we're going to look at the same type of thing. Is the coefficient a positive number or a negative number? That's going to determine everything for our chart here. So if we have an even number as the largest exponent, and the coefficient is positive, such as this one, that's a positive 3, we know the graph is going to go up on the left end. And it's going to go up on the right end. And we saw that in this graph right here. Oh, let's cancel that. This is an x to the fourth. And when we graphed it, it went up on the left end and it went up on the right end. Because it's an x to the fourth and he decides everything. Even if we put 2x to the third minus x squared and minus 7x. All these other ones are trying to do different things to the graph. And they did make the graph look different. But still, because this is an x to the fourth and has a positive coefficient of 1, it's going to go up on the left end and up on the right end. He's still controlling what the graph looks like. Up, up. All right, what if it's a negative coefficient? Well, if it's a negative 3, then the left end is going to go down towards negative infinity, and the right end is going to go down. So if there's a negative out there. So let's look at that graph. All we have to do is change this to a negative. Everything else is already negative, and still it's going up. But the largest one is in charge. When it goes negative, oh, look, now both ends are going down. Both ends are going down because if it was a negative 3, it doesn't matter what the negative number is. The coefficient just has to be negative. And that will turn it to where both ends are going down. Where if it was a positive 3, both ends go up. So again, x to the fourth. Even if we change this to a positive, change this to a positive, change this to a positive, it still goes down on both ends. It just changes what it looks like in the middle. But the biggest exponent is in charge of what the graph looks like. Okay, so that was for an even exponent. Now let's look at an odd exponent. So for an odd exponent, so for example, 3x to the fifth plus x plus 1. Just to throw one out there. This, or we'll even make this like an x squared, just to give it a different number. This is an odd number, right? 5 is an odd number. Very odd. Oh, well. If the coefficient, which is 3, which is a positive number, that means my graph is going to look like this. It's going to go down on the left. And it's going to go up on the right. All because the coefficient is a positive and the largest exponent is odd. Let's take a look at one of those. So if we change this from a fourth to a fifth, I'm going to take away the negative 3. Change this to a fifth degree. So it's odd is the largest one. Oh, look, now it goes. I want to change some of these to minus so it gets a little different in there. There we go. That looks a lot different. X to the fifth. On the left side, it's going down to negative infinity. But the right side is going up to infinity. Zoom in a little bit there. It looks different in the middle. But that's a positive coefficient, like let's put 2. Coefficient of 2. It's a positive 2. So that's how it behaves, as it goes down on the left, up on the right. If a negative coefficient, if this is a negative 3, it's going to turn everything upside down. This is going to go up on the left and down on the right. Let's illustrate that with our graph. Let's just change this 2 to a negative 2. Oh, wow, it's even a pretty smooth graph there. Up on the left end, down on the right end. What it does in the middle is determined by all these other things. Change that to a plus. See, that changes it right there. But up on the left, because this is a negative coefficient, down on the right. All right, so this is great to have in your notes. It's great to have this. So anytime I ask about the end behavior,
do I need to retype it?
End behavior, this chart is what you can refer to, because this is what I'm asking you. End behavior means what's the ends do? The left end and the right end. Up to infinity, down to negative infinity, or does the combination? Left goes down, right goes up. So there you go. We'll double this line here just to divide those up. Even or odd? All right. What else do they want to tell us in this lesson? But that's exactly what this is. Odd degree, even degree, travels in opposite, travels in the same, positive, negative coefficient, down, up. I just put my even on the left and odd on the right. So it says, describe the end behavior of this graph. 16x to the fourth plus x to the third minus 12x squared minus 15x plus 19. All we care about is just the first term because it's the largest exponent. It's a positive coefficient because 16 is a positive number. It is an even exponent. So if it's even, we know it's going to be over here. It's positive. When it's going to be over here, we know both sides will continue up. It's going to look like that. Check the answer. The leading coefficients positives of both ends will continue up. That's all we're asking when we ask for end behavior is to tell me what's there in the red, basically. All right, let's look at page 2. Man, page 1 took a long time. This has a review on the history of solutions of linear and quadratic equations. We've done a lot of that. Did a lot of that in Algebra 1 on solving linear equations. If you have 2x minus 5y equals 8, and you solve that, you got to set the y in for 0. So substitute y for 0 and solve for x. X equals 4. And look, when you graph it, that is the solution. X equals 4. Wherever it crosses the x-axis is the solution. That was true for a linear equation. It's also true for quadratic equations. Look, this is where it crosses. -3 and 2. What are the solutions? The solutions are x equal -3 and x equal 2. All right. So let's look at a cubic function, x to the third. So let's consider what happens to the graph of the parent function when we graph x minus 3 to the third power minus 1. All right, so let's do that. So y equals x to the third was our parent function. But if we change that and graph x minus 3 minus 1 equals x minus 3 to the third power minus 1. As we expected, let's zoom in here a little bit. As we expected, that turning point that was at 0, 0 has now moved 3 places to the right and down 1. There's the turning point now. 3, -1. 3 to the right, down 1 from 0, 0. So without using the table values or any graphing technology, we can tell what it would look like because we know it's going to go 3 right and down 1. So the degree of the function's odd. We knew it would go opposite directions. There's no negative out front, so we know the left side's down, the right side's up. We can kind of tell some basics about it just by knowing the end behavior. And again, we knew the turning point moved over right 3 and down 1. So what's it saying here? Substitute according to that point of inflection to check the solution. So the solution for this, is at 4 because that's where it crosses the x-axis. So I said, anytime you graph it, the solutions to equation are where it graphs there. Now, there may be some imaginary solutions that you won't know. And this one has 2 imaginary solutions because we know from the fundamental theorem of algebra, there's 3 solutions to this equation. It's an x to the third. There's 3 solutions. When we graph it, we only see 1. So either the solution is x equals 4, x equals 4, x equals 4. Maybe it's the same solution 3 times. Or there's 2 imaginary solutions. But we know x equals 4 is a solution to this equation. With quartic, if we graphed -5 times x plus 1 to the fourth power plus 5, without using Desmos, we know that First off, it's going to go down. It's an even degree function. So we know both ends are going to go the same direction. And we know that the direction is down. And we know it's going to be shifted 1 to the left and up 5. The vertex is. And sure enough, when we graph it, 1 to the left, up 5, and both ends go down because of the translations that happen there. And the zeros are -2 and 0. That's the solutions. The solutions are x equals 0 and x equals -2 because that is where it crosses. There may be duplicate solutions of those numbers, or there may be 2 imaginary solutions, because we know it should have 4 solutions when we solve that. All right, keep in mind, not every function has x-intercepts. Does that mean there's not a solution? No, it means there's not a real solution. A later lesson next semester, we may talk more about complex solutions or imaginary solutions. So solutions of polynomial equations, this talks more about it. Find the solutions to this function and use the properties of the polynomial to describe the end behavior. Well, they already graphed it for us when they gave us the function, but we know it's a third degree with a negative, left end up, right end down. Solution is at 1 because we see on the graph, that's where it crosses the x-axis. So if we substitute a 1 in for x, this will equal 0. That'll be a solution. All right. Because 1 minus 2 is -1. -1 to the third power is -1. So -3 times -1, +3 minus 3 equals 0. All right. So then they check the solutions and they get a 0. When they substitute that 1, 0 in there, they get 0. So. All right. Let's see. 4th degree. So we know both ends are going up because it's a positive coefficient. We know it's shifted 6 left and up 1. I'm sorry, down 1, -1. 6 left, down 1. Solutions are -5 and -7. We know the solutions just by looking at the graph. Yippee yay. We check those 2 solutions, -7, -5. It does equal 0. All right. Closing that out. Page 3. I think this is the last page of this lesson. Let's see. Is this where they... There's the lesson summary. Yep. Page 3 is the last page of the lesson. All right. Now we're going to talk about even and odd functions. Like I said, let's not be confused with even and odd exponents. We're going to talk about even and odd functions. Now, there's a way you can tell if a function is an even function or an odd function. Let's put this up, x squared minus 5. Here's what's true of an even function. If it's an even function, it's going to be symmetrical. What's symmetrical mean? It means it's like a mirror on both sides. Like if you put a mirror in the middle, both sides look exactly the same. This one is symmetrical over the y-axis. X equals 0. That purple line, let's make that a different color. Let's make that a red line. So that red line is the y-axis. And you can see the graph is symmetrical. The left side looks exactly like the right side. So this is an even function. An odd function is symmetrical around the origin in a rotation. If you rotate it around the origin, it's symmetrical. So if you see this going up to the left, if we rotate it 180 degrees, it goes down to the left instead of up to the right. Symmetrical. So this is how we determine whether a graph is, whether a function is even or odd. Okay, so we're going to write this down here. This is a different thing than above. Even or odd functions. Different than above. This is different than above. Up here, we're just seeing it if it's an even or odd exponent. Highlight that. Even or odd exponent. This is an even or odd function. Okay, so that's different. So we're talking about something different than that. If we see this equation, we might think it's an odd function because it's an odd exponent. This is not an odd function. This actually, could be even function. This is not. The exponent will not tell you. Okay, so let's talk about even. Let's see, even functions. Adding to our notes here. Even functions. Even functions are symmetrical over y-axis. Symmetrical over the y-axis, which means if we have a graph of a function, if it did this, and then the other side did exactly the same, even function. It is symmetrical over the y-axis. The left side looks like the right side. Exactly. How else can we tell if it's an even or odd function? Okay. Algebraically, f of negative x equals f of x. You're like, what? Let me show you what I mean. Let's actually give an example here. So if we have f of x equals 2x squared plus 5. And we substitute negative x in. So what does negative x equal? Well, that would be 2 times negative x squared plus 5. Right? That's negative x. Just substitute negative x in for any and every x. So let's simplify that. F of negative x. What is negative x squared? Well, that's negative x times negative x. That's a positive. Negative times a negative positive. So that's 2x squared and then plus 5. Wow. So if we look at that and we see that f of x was 2x squared plus 5, negative, when we substitute negative in, it's exactly the same. So this is an even function. That's what it tells us. This is an even function because when we substitute negative x in and simplified it, it's the exact same. F of x, f of negative x, and f of x are the same equation. That's how we know it's an even function. And when we graph it, it's symmetrical over the y-axis. All right. So let's talk about odd functions then. So how would we tell if it's an odd function? Well, odd functions are symmetrical around 0, 0, or the origin. And we're talking about doing 180-degree rotation. So like if we have a graph and it does this. Let's see. That means on this side, if we rotated that 180 degrees, I draw the same graph this way. If we rotate that 180 degrees, it'd be the same.
Thank you, Lily. All right, Maddie. So what? Put my inputs in the cell.
Rotating 180 degrees would be the same. Symmetrical around 0, 0, which is the origin. Like, okay, well, that may or may not be easy to see, depending on the graph. Well, in this,
What does the plant take in? Okay.
for it to be odd, f of x would equal negative f of x. No, pardon me. F of negative x would equal the opposite of f of x. The opposite of f of x. It's like, okay, what are you talking about there? Okay, well, let's do an example for that. If f of x equaled this, let's say, for example, it equals 3x to the third plus x. That's our equation. And we substitute f of negative x into it. So that'd be 3 times negative x to the third power plus negative x. Okay, let's simplify. What's negative x to the third power? Well, negative x times negative x is a positive, but if we multiply that times another negative x, it's back to a negative. So f of negative x would equal 3. Oh, sorry. Since we have a negative there, it's going to be a negative 3x to the third, because that's negative x to the third times 3. So negative 3x third. Plus a negative x would just be minus x. So how does that compare to the original? This was a positive, that was a positive, this is a negative, this is a negative.
First, look at yours. Make sure this is good.
This is an odd function.
Help you. I don't want you to shout out the answer on this one.
So let's see, how would I write this?
Some answers that may help. Okay. William.
All terms.
Of my inputs. How many carbons do I have?
Change signs.
That part that I highlighted blue. How many?
All the terms change signs. They were all positives. Now they're all negatives. If there were some positive and some negative, we'd expect to be some negative and some positive.
One, right?
All the terms change signs, and that would be an odd function. Okay, let me show you one more example. Let's look at this equation. F of x equals, let's call it 3x to the fifth
That's a good question.
minus
Where do all those carbons come from?
2x squared
How many do I have on the right there, Hunter? How many?
minus x
There's 6.
plus
So I have
4.
1 carbon on the left and 6 on the
And
right.
let's substitute
That's a good question.
negative x, just like we did above, to figure out, is this an even or an odd function?
Outside.
So 3 times negative x to the fifth power
It's taking like our breath.
minus 2 times negative x squared minus negative x plus 4. All right, simplify that. Negative x to the fifth power. That's negative x times negative x times negative x times negative x times negative x. That's going to be odd because we have an odd number. Every 2 of them that we multiply together become positive. So we're going to have a positive and then another positive, but then we got a negative.
I don't know, but that's not what
So
we're
this is negative 3x to the fifth. Negative x times negative x, well, that was positive. So this stays the same. It's still negative 2 times x squared. Negative negative x is plus x, and this is plus 4. So what happened? This one changed signs. That was a negative. That was a positive 3. Now it's a negative 3. This was a negative x. That's a positive x. But that stayed negative. That stayed positive. We have a mix. Some changed, didn't. Some changed.
I'm not taking shrugs today. I don't know why you're doing shrugs, but I'm not doing shrugs today.
Some didn't.
Okay, what does this little number tell us? How many hydrogens?
Some changed, some didn't.
And H2. How many
This
hydrogens
is neither even nor odd.
Is that balanced? Good. So you need to give me an example of one of those. So I just gave you two.
Most equations are generally going to fit into this.
5A wants to know, is it balanced?
But this is how we know algebraically. Now, graphing, we know it's symmetrical of the y-axis or rotation symmetrical around the origin. If it's neither one of those, it's also neither even nor odd. It has to be these to be even or odd. Or algebraically, we have to be able to substitute negative x in and get the same function, the exact opposite function. Or if you get a combination, it's neither. So I'll take a picture of this after class and put it in Google Classroom. But this is great for your notes. And you should write that down in a way that you understand it. If you don't understand my terminology, if you understand what I'm saying, write it in a way that you understand. But it has to be the same, exactly the same to be an even function. Exactly the opposite. Positive, negative, to be odd function. But if it's any kind of mixture, it's neither one. All right, so there's all of our notes we've taken today on that subject. All right, so here's where they talk about it. This is symmetrical over the y. This is not, because look, the y's over here. This shifted one to the right. It's not symmetrical over the y anymore. So this is a neither function. This one's even. This one's neither. If we look at this, this is 180-degree rotation around the origin. This is an odd function. This one, the origin's over here. If we rotate that around 180 degrees, it's going to be up over here somewhere. It's not going to be an odd function because it's not symmetric around the origin. And again, they did the work here. The x to the third is an odd function because it ended up exactly the opposite. This one, when we shifted it over one, you had a combination of stuff. Some's negative, some's positive. No, it's all negative in the final, but some of it was positive, some of it was negative at the original. It's neither one. All right, just looking at a graph. Is that even, odd, or neither? Oh, what do you think? We don't have the equation, so we can't substitute negative x in. All we have is a graph. If that was rotated 180 degrees, would it look exactly the same? If I turn that graph upside down, would it look any different than it does now? If it's rotation, and it is symmetrical rotation, that's odd. So this is an odd function because we'd have to rotate it for it to be the same graph. If we reflect it over the y-axis, then it would be even. But that means since this goes up over here, that means it would go up over here as well. It would look the same on the left as it does on the right. This doesn't look the same on the left as it does on the right. But if we rotate it 180 degrees, it's still the exact same graph. So that's odd. See what it says right here? Odd. Yeah.
We're from 5B. So you're drawing a model.
Then it gives an equation where you can test to see, is this even, odd, or neither? Well, if we put negative x in, that's going to be positive x to the fourth because it's being times 4 times. If you put negative x in here, negative x squared is going to be a positive x. So that's going to be the same. And that's going to be the same. So this should be an even function because everything is the same. It ends up exactly like it started. If we simplify it, it's the same equation, even. So there's our lesson summary, guys, for the 4.03. 4.04 is a little shorter. It won't take as long. But there's the top of our notes. And here's a summary of what we put on bottom. I put a lot of examples in the notes on the bottom of ours. So that may help you more than just this summary. But if negative x equals the same as the x in the equation, it's even and it has symmetric around the y-axis. If it's exactly the opposite, all the signs changed, it's odd, and it'll be symmetric around the origin, 180-degree rotation. But if that's not true, then it's neither one. All right. There are some practice problems that they give you. Oh, I guess I can look at those. I went to the assignment. Let's look real quick. I'm not going to take the time to do them because they tell you the answers. So if you don't get it right, they tell you the answer. It says completed the exercise. Check my work. Describe the transformation by just putting a negative 6 on the end. What's that do? Well, we know that goes down 6, right? So you check it. It's a 6-unit downshift. What's this transformation? What happens when we put a 16 out front? It just makes it more narrow, right? It goes up faster. What about if it's a negative and a number less than 1? There's a second set of problems to practice. Find the solutions to each of the equations and put it x equals negative 5. That's a solution to which one? Well, what's the easiest way to find that? This lesson was talking about graphing. So if I graph this, let me graph this equation here. I wonder if it'll copy and paste.
Okay, and then what does it give
just
us?
To show you how to do that. So if I make that to the third,
So look at Maddie's going. Yep, Maddie's getting there.
that's squared.
Maddie has the
Okay, there I graphed it.
sun.
So what's the solutions? The solutions are negative 5, negative 3, and negative 1.
Like a cat. I love it. Let me see.
Negative 5, negative 3, negative 1. That's the solutions. I don't like what makes that black. It's hard to see the black on the black. Let's do green. Yeah, negative 5, negative 3, and negative 1. So, negative 5 is one of the solutions for that one. I just knew it by graphing. Wherever it crosses the x-axis, that's a solution. X equals 1.72. That's not going to be this one because we know the solutions are negative 5, negative 3, negative 1. So you should graph the other two and see which one has a 1.72. All right, let's go to the assignment. I won't look at all the rest of the practice problems, but they're there for you. How does the graph of x plus 2 to the third power minus 7 compare to just x to the third? There's 2 translations there. What are they? Did it go left 2, right 2, up, down? Which way to go? How does this transformation compare to just x to the fourth? And you can graph both of those if you want to compare on a graph. If you don't know by looking,
I can tell.
Graph it, play with it. Without using technology, without graphing this, can you tell me the end behavior? Again, this big boy at the front here, he's the biggest exponent. He determines what that graph looks like. So you can look at your notes and tell negative 3x to the fourth should tell you all you need to know what happens. And then look at this. Is this even or odd? Is this even or odd?
Take a picture of it.
Apparently it's one or the other because they don't give you neither as an option. It's either even or odd and why. Okay. And then this would determine whether it's even or odd, and they just give you the equation. So you have to substitute that negative x in there. All right. 5 questions. Let's go to 4.04. Look at our last lesson today. Solving and graphing polynomials. Well, we've been graphing polynomials, so we're just adding a little bit to it. Let's look at x to the third plus 3x squared minus 22x minus 24. It's like, man, the zeros of that would be tough. I'd have to factor all that out and get it there. No, when we graph it, the solutions are -6, -1, and 4. We don't have to do all that factoring. Now that tells us what the factors would be x plus 6, x plus 1, and x minus 4. That would be 3 factors of this x to the third equation. So we do know the factors because we know the solutions. So there it is, x minus 4, x plus 1, x plus 6. Because of, you can substitute those in and work backwards if you need to, but this is how they check them. Since it says 4 is a solution here, 4 is a solution. If you substitute 4 in there, it does equal 0. So that is a solution. That is a 0. But the graph confirms that. We don't really have to do the substitution. So it's just letting you know how easy it is to find graphing the zeros. Determine the zeros of x minus 2 times x minus 5 times x plus 1. And describe the end behavior. All right, that one we will look at on paper just to confirm a few things and how this works. So that said x minus 2, x minus 5, and x plus 1. Okay. Let's know end behavior and what are the zeros. Well, the zeros are where those equal 0. Where does x minus 2 equal 0? When x equals 2, right? Because 2 minus 2 equals 0. So we know 2 is a solution. Where does this equal 0? X minus 5 equals 0. Plus 5, x equals 5. No surprise that when x is 5, this equals 0. Because 5 minus 5, how about this one? I don't even think we have to do this. When would that equal 0? That would equal 0 when x is -1. Because -1 plus 1 is 0. So this is the zeros. That's also the solutions. That's the same thing. Sometimes we call them solutions, sometimes we call them zeros. It's also the x-intercepts. These are all words for the same thing. And it says describe the end behavior. Well, the end behavior, if we multiplied this together, here's an x, here's an x, here's an x. They're all to the first degree. So if we multiply those together, we got an x to the third. And this is 1x times 1x times 1x. So 1 times 1 times 1 is just 1. So the coefficient is a positive 1, x to the third. We know a positive coefficient with a third is down on the left, up on the right. That's our answer. Down the left, up on the right. And here's the zeros. If we're not sure, let's graph that. Y equals x minus 2, x minus 5. You can graph it in factored form, x plus 1. Oh, look, there's the 3 zeros, -1, 2, and 5, just like we had on ours, -1, 2, and 5. And we said it went down on the left and up on the right. Oh, look, it goes down on the left and it goes up on the right. We knew that before we graphed it because we knew x times x times x is this is an x to the third equation. Now, we could have went ahead and multiplied all these together and got the entire equation. You know, maybe the whole equation was x to the third minus 10x squared plus 2x plus 10. I don't know. I didn't do that. But I didn't do that because I didn't care. Because it didn't ask me for that. It asked me the end behavior, which this is all I need. I don't need any of that. And it asked me the solutions, which I could get right here. So I didn't bother doing all that work of distributing the x and distributing the -2 and then multiplying that and distributing it to x plus 1. That's a lot of work that is unnecessary because all I care about is the biggest exponent term and the solutions. So save yourself some time when you don't need that. Don't do that. Here's one that has 4, x plus 2, x plus 3, x minus 1, x minus 3. Well, we know it's going to have 4 solutions, so it's going to be an x to the 4th because x times x times x times x, x to the 4th. And we know what the solutions are. They're negative 2, negative 3, because negative 3 plus 3 is 0, 1, and 3. Negative 2, negative 3, 1, and 3. And when you graph it, that's where it's going to cross the x-axis at those 4 locations. Here's another one. This is a little trickier, so I do want to play with this one real quick. And then we're about to wrap up here. This may look a little more complicated, but it works the same way. What is the solution there? X equals what? Well, if we take 2x minus 1 and set it equal to 0, add 1, 2x equals 1, divide by 2, x equals 1/2. 1/2 is one of our solutions. If we graph this, it will cross the x-axis at 1/2. What about here? Negative x plus 3 equals 0. Subtract 3. Negative x equals negative 3. Divide by negative 1. X equals 3. If we did this, we'd find that x equals 4/3. That'll be a fraction as well. So there's our 3 solutions. What would be our end behavior? Well, if we multiply this times this times this, that's going to be our largest term in our equation. So 2x times negative x equals negative 2x squared. So that's those two. And then multiply it by the 3x, negative 6x to the 3rd. So it's a 3rd degree and it has a negative coefficient. So that means it's going to go up on the left and down on the right. Up on the left, down on the right. Let's take a look at that real quick. Up on the left, down on the right. There's that 1/2, 4/3, and 3 solutions.
Why?
See if we got another one right here. What else are you going to go? Multiplicity. That's the last thing we need to cover here. So let's do it on decimals. I think we can do this real nice. All right. See, when we graph x minus 2, x minus 5, x plus 1, we got the solutions, right, of 1, 2, and 5. But what's the graph look like if this is another x minus 2? Look, there's 2 x minus 2s. It still just touches the x at those same places. Negative 1, 2, and 5. It's like, oh, there's only 3 solutions. That's true. There is only 3 solutions, but there's actually 4 because this is a solution twice. X minus 2, x minus 2. That means there's 2 solutions that are equal to 2. If a graph has multiple solutions that are the same number and it has an even number, it's going to bounce off the x-axis. Notice that did not cross the x-axis. If we zoom in, it does not cross it. It bounces off of it. It just touches it. That means there's 2 solutions. Or maybe there's 4 solutions. Here, let's make 4 of them. Now there's 4 of them. X minus 2, x minus 2, x minus 2, x minus 2. Still, it just bounces off of it because there's an even number. Let me take 2 of those off. Even number. If there's an odd number, that's going to be harder to tell because x minus 2, it'll still cross. Now, it kind of crosses like an x to the 3rd equation. But multiple answers can cause it to look a little different when it crosses the x-axis. If it's even, the important thing to remember, if it's even, it'll bounce. Here, let's just write that in our notes. For multiple solutions,
we're going to kind of split those up today.
like f of x equals x minus 2 times x minus 2 times x plus 5. Let's just do that.
Give it a vote. If you don't vote, Ismo.
The graph bounces off the x-axis. For multiple solutions, the graph bounces off the x-axis. So for this one, at 1, 2, 1, 2, 3, 4, 5. Right, so this would go up here and it would come down and bounce off the 2. Example. X minus 2, x minus 2, x plus 5. The negative 5 is the solution and it crosses it. There's 2 solutions at 2, so it bounces off of it. That's what this part of our lesson is telling us right here. See, that has more than one solution at negative 1. It has 2 or 4 or 6. It looks like 2. At 4, it gets flatter. So x plus 1, x plus 1. Bounces off at negative 1. So you'll see that anytime you're graphing with multiple solutions, that the graph will bounce off at that location. Let's see. Given this cubic and one of the roots is there, find the other roots and plot it. Well, you can take long division and divide that x plus 5 out of there and then factor that quadratic. Of course, you can also graph it and find the other solutions. Same thing with the quartic function. This is as a root of x equals 2 with a multiplicity of 2. So you know when you graph that, it's going to bounce off the graph at 2 right there. See, it bounced off the graph at the x-axis. All right. Oh, there's another page of this. Hold it. I thought we were at the end of this. Make sure there's nothing else important we're missing. Average rate of change, increasing versus decreasing, minimums and maximums. We've talked about that several times. The average rate of change is the slope. So if we look at this graph here, what is the average rate of change between x equals negative 1, x equals negative 1, and x equals 2? Well, here's where the graph is, and here's where the graph is. That's a slope of 0. The average rate of change is 0. Even though the graph goes down and up and down and up, between those 2 points, they're the same. Now, if I said what's the average between 2 and 5, or 6, we'd have to go way up to where 6 is and draw a straight line between there. What's the average rate of change? Let me take some of this out. Change this. So if we're doing the average rate of change between 1 and 2, at 1, the graph is up here at 8. At 2, it's down here at 0. So what's the average rate of change between there? Negative 8. At 1, it was up here at 8. At 2, it was 0. So it obviously a straight line where we have slope of negative 8. And then it talks about increasing and decreasing. Well, this is increasing all the way until x gets to 0.26. 268. Then it's decreasing all the way until 3.732. And then it's increasing again, right? Because the slope is getting smaller. The y's are getting smaller in between 2.68 and 3.72. The y's are getting smaller that whole time. The y's are getting bigger after that, and the y's are getting bigger before that. So that's the increase and decreasing. And of course, this is a maximum. This is a minimum, because on both sides of it, it's the largest y. On both sides of this, it's the smallest y. See, that's a minimum. Maximums, minimums. So that's what these are talking about. If you get confused by that, go back and review this. Maximum, minimums, right? Increasing, decreasing. It has all of that. So in this, it says, what's the average rate of change between x equals -1 and x equals 1? Well, where is it, -1? When x equals -1, this equals -4. When x equals 1, it's up to -2. So what's the slope between -4 and -2? It goes up 1 over 1, up 1 over 1. Oh, that's a slope of +1. That's the average rate of change, 1. It says, and locate the local maximums and minimums. Well, there's a local maximum at 0, 0. There's a local minimum at 2, -4. Now notice it's not the maximum because it goes to infinity, but locally in that area of the graph it is. So check your work. It says average rate of change is 2 over 2, which equals 1, because it goes up 2 and over 2 between those 2 points. And then it has increasing, decreasing.
All right.
Increasing, decreasing, increasing.
Just for right now.
Lesson summary. There we are at the end.
So number 2, at what time of the year?
Okay, so it's talking about the solutions. It's where it crosses the x-axis. That's the roots, the solutions, the zeros, the x-intercepts. And in behavior, you look at this chart that we have in our notes. Rate of change is just take the 2 points and use the rate of change formula, or count rise over run on the graph. All right, here's the assignment. What are the zeros? Oh, and it gives you the factored form. Well, I'll tell you the first one is 5, right? That's the first zero. 5 minus 5 equals 0. X equals 5. Of course, that's the same on all the answers. One factor of this is x minus 5. What are the zeros? Well, if it's me, I'd probably just graph that and look and see where the zeros are. Calculate the average rate of change between 0 and 1. So graph that and count rise over run between where x equals 0 and x equals 1. What's the average rate of change between x equals 0 right there and x equals 2 up here? Rise over run. Count the rise, count the run, simplify the fraction. That's the slope between those 2 points. And what are the zeros of this function? They gave you the graph. All you have to do is look at it and say, what are the zeros? Where does it cross the x-axis? And that's it. 5 problems. All right, guys. Phew, about an hour and 15 minutes today. That is the last of our assignments. All we have left is the final after this. Everyone has to take the final. So get these done, and then we'll be talking about the final next week. So
Okay, thank you.
all right. Have a great week, guys.